All right, so our first presenter for this afternoon is Sara Griego, who joins us from UC Santa Cruz this summer. Sara's been working with Brenna, and today we'll hear about their project together, Fast Blue Optical Transients as Intermediate Mass Black Holes Eating Stars.
Thank you, Gwen. Thank you, everyone, for being here this afternoon. The big question of my project is where are the intermediate mass black holes that supermassive black holes must have grown from? So we know that supermassive black holes formed from accretion and mergers of lower mass black holes, but we don't observe the number of these lower mass black holes that we would expect, this intermediate mass range. So here I have a plot of the black hole mass function, and on the right, specifically on the right of this gray bar, you can see the supermassive mass range, and you can see that the function is decently constrained in the supermassive range, but as we move to the left of that gray bar into the intermediate mass range, the uncertainty of the black hole mass function expands greatly. We have not observed many of these intermediate mass black holes for a few reasons. One is telescope resolution limits. We can't resolve the spheres of influence of these lower mass black holes. We simply don't have the ability to do so. And then also most black holes are not accreting, and so they are simply dark. And but one way that we can hope to find these intermediate mass black holes is when they tidally disrupt a star in a tidal disruption event. So a tidal disruption event happens when a star, which is a little hard to see, but it is right there, gets too close to the black hole it's orbiting and is torn apart, and it creates a debris stream. And as that stream falls back into the black hole, it lights it up and creates this observable flare that we can use to see these black holes, which would otherwise be dark. One note I want to make is that in this simulation, this stream is not the bright thing that we are observing. We are observing as the matter is being fed back into that black hole. So the mass fallback timescales are dependent on the mass of the black hole. So the timescale will be shorter for a smaller black hole, and it will be longer for a larger black hole, and it goes as t goes as mass to the 1/2. And so we would expect that if we had if we were looking for an intermediate mass black hole with a smaller mass, we would expect a short time scale. And so there's this new class of transients called fast blue optical transients, which have these short time scales that we're looking for from an intermediate mass black hole tidal disruption event. So the green dots on this plot are fast blue optical transients as of 2019. And this is showing them against other transients such as supernova and superluminous supernova. And these are characterized by having very short rise times and very blue spectra, which I'll touch on again later. And these also have, we're specifically focusing on the most luminous of these events in the black box at the top. The 3 in pink are the ones that I have already fit this summer. And the 2 in green, which may be a little bit more difficult to read, but they are AT 2018 Cow and Dougie. These are more well-known transients that have already been fit in this way, but I am fitting the 3 pink ones for the first time. So it is important to know that in the last few years since that plot was made, we have an update to some of these FBOTs, fast blue optical transients, and they have been classified. Some have been classified as different types of supernova, but the general region of that black box that I pointed out earlier are these cow-like, in reference to 2018 cow, fast blue optical transients, and their origins are still uncertain, and there's still some disagreement on what those might be. And as I mentioned earlier, an important feature of these transients is their spectra, and so I wanted to explain the blue of fast blue optical transients using the spectra of the main event that I focused on this summer, AT 2018 WPP, and show that in their spectra, it stays very blue, very luminous at these blue wavelengths, even at late times, which is not a characteristic that a supernova would have. And this specific one is also very featureless. It doesn't have many spikes in like you would expect from a supernova, and this is one of the things that helps us decide what would be a better candidate for an intermediate mass black hole tidal disruption event. So as I mentioned, this is the transient that I focused on initially this summer, And here is a plot of the data of that transient, and each of the colors represents a different observing band. And one thing that we also wanted for these transients that we're fitting is for them to be observed in the UV, which are the top 3 bands here. And this was the best option outside of the 2 that had already been tested as intermediate mass black hole tidal disruption events. So it has this short rise time of less than 10 days, and it is very luminous. And so how am I going to model this event? I used a fitting code called MOSFIT, which is a Python package that fits and estimates the parameters of transients. And it uses a Markov chain Monte Carlo, or MCMC, and also a nested sampler option, which we found had consistent results with each other. And this it assumes a black body photosphere, and it also assumes that it assumes that these black holes will be Eddington limited, meaning that they have this is some limit on their luminosity. The Eddington limit is when the force of radiative pressure moving away from the black hole and the force of gravity in towards the black hole are in equilibrium. And so the Eddington luminosity scales directly with the mass of the black hole. So if we have a very luminous object, we're going to expect a very large mass. So if we go back to the data I showed earlier of this AT 2024, and we try to fit it using MOSFET and all of these base assumptions, we get a fit that doesn't work. We find that the fit, which is the lines in the back, is the completely wrong timescale, and the resulting mass is supermassive at 10 to the 6.7 solar masses. And so this is an Eddington limited model, so we're giving it a very luminous event, and since luminosity and mass scale together, it says that this has to be supermassive. And as I mentioned previously with the fallback timescales, if you have a supermassive result, then you're going to have a longer timescale. And so that's why this is stretched nearly horizontal across the short timescale of this FBOT. And so my mentor and I discussed it and decided to relax the Eddington limit parameter, and essentially allowing these to give us super Eddington results, and the fit improved drastically. This is well fit in all bands, and the result is 10 to the 5 solar masses, which would be an intermediate mass. And so with this super Eddington model, we fit 2 more transients, and these both also fit quite well and resulted in black hole masses between 10 to the 4 and 10 to the 5 solar masses. And one really interesting thing about specifically the CSS 161010 is that this is a nuclear transient from a dwarf galaxy, and the mass that we found in our initial results is consistent with predictions for the central black hole of this galaxy using galaxy scaling relations. And so what does it mean if these FBOTs are in fact intermediate mass black hole tidal disruption events? This would allow us to probe the intermediate range of the black hole mass function. So on the left, I have a histogram of the masses that the MCMC returns for the 3 transients I fit this summer. And I'm showing this range of masses here on the black hole mass function to show the range that we would be able to see with these should they be intermediate mass black hole tidal disruption events. And we can use the rate of these transients in the future to constrain the black hole mass function more. So in summary, the selected luminous FBOTs are being well modeled as tidal disruption events by intermediate mass black holes. These black holes would be super Eddington, and the result for the CSS 161010 transient are consistent with predictions for the black hole mass. And our next steps, we're going to run all fits to convergence, which we don't anticipate will change our results much, but will just be, a stronger result. We will fit more FBOTs that match selection criteria, either as they are discovered from projects like LSST, and also fit those more well-known transients that I discussed earlier, AT 2018 Cow and Dougie. I will be fitting those myself for the sake of consistency. And also conduct analysis of the photosphere characteristics of these black holes so that I can like, have a good reasoning for the behaviors and characteristics that we're seeing. Thank you.
All right, questions for Sara? Someone pass the mic over to Jess.
Awesome, Sarah. I'm curious about the next steps. How many of these do you think will you be able to like find and use to constrain those that frequency?
That is a great question. I unfortunately do not know the answer to that. I don't know if that's something that I could know. I am open to having you weigh in on this because I also am curious.
The rates are still relatively uncertain, but there's a rates paper, it's like 0.25% of core collapse or something like that.
Cool. Okay. Great. Thanks.
Thank you.
Or actually,
So my question is about the accretion rate being super Eddington. Is this typical of other TDEs, or is this specific to this class that you are finding this requirement for it to be super Eddington?
I have not discussed that with my mentor. I know that it is what we discussed, like about to expect from these, that it wasn't unreasonable that they would have to be super Eddington to be this bright, but I don't know if it's typical for like TDEs by supermassive black holes. But I could definitely look into that.
Until this, then a little bit more. Why is it expected for these to be super Eddington? Maybe we can follow up later.
Yes, I definitely talk later.
Let's do that.
Thank you.
Right, did you also have a question? No?
is it okay to do that?
Yeah, that's fine. Okay.
Okay, thanks. Yeah, I had a similar question. I was just curious how super was super Eddington? Was it like 1%, 10%,
Yes.
factors of 100 or something?
So there was a range, and I have a plot for that, but just for a visual. But so the CSS was around 16 times Eddington, and then we got a really large one for the brightest one, which was closer to 60 times Eddington. So large range. And we're still discussing why that might be and what explanations could be like.
All right, let's thank Sara again.